This is Satyajit Raj from Government Degree College Begumpet explaining you organic chemistry. Now let us discuss the applications of inductive effect. First application is acidity of carboxylic acids. First application of inductive effect is as it discusses gives the explanation for the acidity of carboxylic acids. As the any group or atom showing plus inductive effect decreases the acid strength as it acquires negative charge on the carboxylate ion, holds the hydrogen atom firmly, and alkyl group that having positive inductive effect positive as the positive inductive effect increases, what happens? The acidity of carboxylic acid decreases. That is, here, why the carboxylic acid? Let us discuss about this one here. So, the acidity is nothing but tendency to lose the proton. Acidity is nothing but tendency to lose the proton. So, as this tendency decreases, as this tendency to lose the proton decreases, acidity decreases. Now, let us discuss here. Here are see carboxylic acid group O and O minus OH. This is the carboxylic acid group. Okay. Now, when it releases H plus ion, it becomes R carboxylate ion. It becomes a carboxylate ion like this. Carboxylate ion. The stability of the carboxylate ion decides the acidic nature of the carboxylic acids. So this negative charge on the oxygen atom, as it gets stabilizes, the acidity increases. See here, the positive inductive effect groups, the group which supplies the electron density, that is alkyl groups. As the alkyl group increasing, alkyl group is having a tendency of releasing electron density. So as the alkyl groups are sending the electron density on this carbon atom, what happens? Here, as the electron density is increased on this carbon atom, due to the this electron density again supplies on the oxygen atom, which is already having a negative charge. So the negative charge increases. As the negative charge density increases on the carboxylate ion group, it becomes destabilized. So it becomes destabilized, and so as the stability of the carboxylate ion decreases, the tendency of losing H plus ion of the carboxylic acid decreases, because the reaction moved towards the backward direction. That is, carboxylate ion tend to attract the H plus ion and move towards the to form the carboxylic acid group. So what happens, as the electron density, as the electron releasing groups increasing, that is alkyl group increases, what happens, as the electron releasing group increases on the carboxylate group, carboxylate ion group, then what happens, the acidity decreases. Here formic acid, for the formic acid here, the carboxylic group, the COOH group is having only single hydrogen, whereas as here CH3 group, alkyl group is increased. Here C2H5, as the alkyl groups is increasing, C3H7, as the alkyl group is increasing, the tendency of releasing electron density on the carboxylate group increases. So the carboxylate ion stability decreases, and which makes the reaction backwards and stabilizes the carboxylic acid group. This one, carboxylic acid group, is stabilized. The reaction move towards the backward direction, and stability of carboxylate ion decreases, which makes the decrease in the acidity of the carboxylic acids. Now, Now, the positive inductive effect increases. As the positive inductive effect increases, so the acid strength decreases. The formic acid obtained, so alkyl set, is most acidic among these acids. Okay, because of that, formic acid, which is having only single hydrogen atom, it is having more it is acting as a strong acid compared to other carboxylic acids. Okay, now the group or atom having negative inductive effect. Suppose these are all the alkyl groups are what? Alkyl groups are showing the positive inductive effect. As the positive and the inductive effect increases, the acidity decreases. Just now I have explained you. The opposite to that one, next is negative inductive effect. As the negative inductive effect group increases, as the negative inductive effect on the carboxylate ion increases, then which makes the acid more, which makes the acid to act as a stronger acid. So the it increases the acidity of the carboxylic acids. Now here, because of increase of negative inductive effect, the increases the acid strength. Negative inductive effect. Now let us discuss with the example here. Now here, carbon trichloro trichloroacetic acid. The chlorine atom is having minus inductive effect. That is, electron, it is acting as electron withdrawing group. So the carboxylate ion which is formed, will be stabilized. The negative charge will be neutralized. The negative charge will be neutralized because of electron withdrawing group. So as the number of electron withdrawing group is increasing, acidity increases. So because of that, here three chlorine substituents are there, which makes the trichloroacetic acid as strongest acid here compared to dichloroacetic acid. And for the acetic acid, no electron releasing groups are there, only alkyl group, that is CH3 group, acting as electron donating group. Because of that, donating group, because of that, what happens? Acidity decreases for the acetic acid. Whereas with the introduction of chlorine atoms on the chlorine atoms are acting as electron withdrawing group. As the number of chlorine atoms increases on the methyl group, alpha methyl group, the acidity increases. That is, here, as the electron withdrawing group increases, acidity increases. Okay, so minus inductive effect is added, so acid power increases. Okay, now the next is strength of benzoic acids and alipatic carboxylic acids. Let us discuss the strength of benzoic acid. Let us discuss the comparison between the strength of benzoic acid and alipatic carboxylic acids. We know that alkyl groups are electron donating groups. That is, it shows alkyl group shows positive inductive effect, means electron releasing group. Whereas the phenyl group, that is C6H5 group, phenyl group C6H5 group is acting as electron withdrawing group, that is showing the negative inductive effect. The reason is in the phenyl group, all the carbon atoms are sp2 hybridized. As the yes, because of sp2 hybridization, the as the s character increases, the electronegativity increases, and as the electronegativity increases, it acts as electron withdrawing group. Because of that, phenyl group act as and shows act as electron withdrawing group and shows the negative inductive effect. So the positive inductive effect decreases the acidity. The positive inductive effect decreases the acidity because it supplies the electron density on the carboxylate ion. As it supplies the electron density on the carboxylate ion, because of excess of electron density, the carboxylic acid unable to lose the proton. So because of that, carboxylic acid decreases its tendency to lose the proton, and which makes the carboxylic acid to show lesser acidity. Whereas here the phenyl group, which is having minus inductive effect, that is electron withdrawing group, it is acting as electron withdrawing group. The phenyl group is acting as electron withdrawing group. It stabilizes the carboxylate ion, which is formed after the release of proton. So as the stability of the carboxylate ion increases, the which makes the carboxylic acid group to release the proton. So the acidity increases with the addition of minus negative inductive effect groups, that is electron withdrawing groups. Okay. Now, hence, the benzoic acid is stronger acid than alipatic acids. In the alipatic acid, alkyl groups are there. Alkyl groups are showing positive inductive effect, which is destabilizing the carboxylate ion. Okay. Hence, the order is for exceptionally the formic acid, that is HCOOH, is having more acidic nature compared to alipatic acid. In the alipatic acids, formic acid, then benzoic acid, and alipatic acids are having lesser acidity compared to benzoic acid. Okay. Now, decreasing order of acidity. Now let us discuss the decreasing order of acidity. Now, we know, just now we have discussed here electron withdrawing groups. Electron withdrawing groups increases the acidity. Greater the power of electron withdrawing group, greater will be the acidity. As NO2 is a stronger electron withdrawing group compared to fluorine. It is NO2 group acting as strong NO2 group. Acetic acid substituted with the NO2 group act as a stronger acid compared to fluoroacetic acid. Compared to chloroacetic acid, the chlorine is having lesser electronegative and electron withdrawing tendency compared to fluorine. Here bromine, because your bromine is having lower electronegativity compared to chlorine. So acidity decreases as the electronegativity decreases, as the tendency of attracting the electron density, as the tendency of attracting or withdrawing the electron density decreases, acidity decreases. So NO2 substituted, NO2 nitro substituted acetic acid is the stronger acid compared to other acids. Okay, in this series, the next series is trifluoroacetic acid, trichloroacetic acid, and tribromoacetic acid, and triiodoacetic acids. Now, because all the in this series, all the carbon is substituted with three halogen atoms, and in this halogen atom, fluorine atom is having highest electronegativity. Because of that, here trifluoroacetic acid is a stronger acid compared to trichloroacetic acid, and tribromoacetic acid, and triiodoacetic acid. As the electronegativity decreases, as the electronegativity decreases, acidity decreasing in the same order. Now, let us discuss for the alcohols. Let us discuss the same type of trend in the alcohols. Methyl alcohol, here this is the methyl alcohol, ethyl alcohol, isopropyl alcohol, and tertiary butyl alcohol. Here, with the in the tertiary butyl alcohol, the tertiary butyl alcohol means it is having more number of alkyl groups. Tertiary butyl alcohol is having more than 3 methyl groups on the carbon atom. As the methyl groups, are electron donating groups that just now we have discussed. That is, alkyl groups act as electron donating groups, whereas it shows the positive inductive effect, acidity decreases. So tertiary butyl alcohol is having lesser acidity compared to isopropyl alcohol, and compared to ethyl alcohol. As the alkyl groups are absent, as the alkyl groups are lesser, the alkyl groups acidity is stronger. Now, as compared to water, phenol is more acidic, but methyl alcohol is less acidic here as compared to water. Here, as compared to water, phenol is more acidic. The reason is in the phenol, the C6H5 group, that is phenyl group, is electron withdrawing group. The phenyl group is electron withdrawing group. Here, water HOH, simple, normal. Here, methyl group is having electron releasing group. Okay, when we are comparing with the water, here hydrogen is substituted with the alkyl groups. Alkyl group is electron withdrawing, and phenyl group C6H5 group is electron withdrawing. So this is the one of the best example to discuss about the how the inductive effect is acting over the acidity. Okay, that is, as the electron withdrawing group is present, the acidity increases. That is, the phenol is having a more acidity. Now here, with the addition of the alkyl group, that is CH3 group, acidity decreases. That is, methyl alcohol is having less acidity. Now let us discuss few examples based on acidity. Now here, as the higher the pKa value, as pKa value increases, acidity decreases. Here, this is the acetic acid with all hydrogen atoms on the methyl group. With the as the one of the hydrogen atom is substituted with the iodine, here bromine, here chlorine, here fluorine. As the fluorine is having more electronegativity, as it is having more acidic nature and lesser pKa value. Here, chloroacetic acid is having 2.8 value of pKa value, and as the pKa value increases, acidity decreases. So here fluoroacetic acid is a stronger acid compared to acetic acid, and the acidity increases in this way. Okay. Now next is, as the substituted bromine atom moves as the distance from the carboxylate group, as the distance from the carboxylate group increases, acidity decreases. Here the carbon, which is the bromine atom, is very close to the carboxylate ion. So here it is having lower pKa and more acidic nature. As the bromine atom, as the bromine substituent is moving away from the carboxylate group, as it is moving away from the carboxylate group, here acidic nature decreases, okay, and pK value increases. So the acidic nature increases in the same way. Now let us discuss some examples. Write the following molecules in the decreasing order of acidity. Here acetic acid and butanoic acid, formic acid and propanoic acid. In these examples we have to write these molecules. We have to write these molecules in the decreasing order of acidity. Here we know that as the alkyl groups are increasing, here formic acid is not having any alkyl group. As the alkyl group is increased, that is CH3 group is increased, this one is having less acidic nature compared to formic acid. So C is greater than A. Then propanoic acid, then butanoic acid. So the answer will be that is formic acid is greater than acetic acid, propanoic acid and butanoic acid. So the order is C, A, D, B. C, A, D and B. Butanoic acid is the least, it is having a very least acidic nature. Okay. Now the next example is here propanoic acid, formic acid, and here alkyl group is increased here, here and here. Now here also the same concept, as the alkyl group is increasing on the alpha carbon atom. When this hydrogen atom is substituted by the alkyl groups, acidic nature decreases. That is, so formic acid is having the highest acidic nature, followed by acetic acid. Formic acid is having highest acidic nature, then acetic acid. Acetic acid, as these hydrogen atoms are substituted by the alkyl groups, the acidic nature decreases. So the order is B is highest acidic in nature, then comes to E, then A, then C and D. So B, E, A, C, D. So the order is like this: B, E, A, C, D. Okay. Now let us move. Now let us discuss the next example. That is here, as the double bond or triple bond is introduced between the two carbon atoms, the acidic nature increases. That is, here the triple bond is between the two carbon atoms, which makes the carbon atom more electronegative due to the increase in the S character in the sp hybridization. due to the increase in the S character in the sp hybridization, as this carbon is sp hybridized, the S character is increased. As the percentage of S character increased, the electronegativity of the carbon increases. As the electronegativity increases, electron withdrawing group becomes stronger and the acidic nature increases. So B option is having a higher uh, electron withdrawing strength. So uh, B is having a highest acidic nature. Then comes to A. Then comes to C. So the option will be B, A, C. Now let's move to the next question. Is here propanoic acid and butanoic acid, fluorine substituted with the on the carbon atoms of the butanoic acid. As the fluorine atom, which is acting as electron withdrawing group, as this electron withdrawing group is near to the carboxylic group, acidity increases. As the electron withdrawing group is very near to the as carboxylic group, acidity increases. As the fluorine atom, that is electron withdrawing group, is moving away from the carboxylate group, acidity decreases. So the option will be B is having a highest acidic nature compared to D, then comes to C and A. B, D, C, A. B, D, C, A. The D is having the least acidic nature, as it is this molecule butanoic acid is not substituted with the electron withdrawing group. Now let us discuss the next example, that is bromoacetic acid, fluoroacetic acid, iodoacetic acid and fluoroacetic acid. Here the fluorine is having a more electron withdrawing electronegativity, so it is acting as stronger electron withdrawing group. Then comes to chlorine, acting as electron withdrawing group, then bromine, then iodine. So the options will so the correct order will be B, uh, B, D, A, C. B, D, A, C. B, D, A, C. This is the decreasing order. Okay. B, D, A, C. Now let us discuss. Write the following molecules in the increasing order of acidity. That is, here the question is trifluoroacetic acid, difluoroacetic acid. As the number of electron withdrawing group, that is fluorine atoms are increased, acidity increases. As the electron withdrawing groups increases, acidity increases. So the options B, A is having a highest acidic nature, then comes to D, then comes to C and B. So the options are, correct order is A, D, C, B. Now let us discuss the next application, that is basicity of the amines. Amines are the organic compounds which are formed by the substitution of alkyl group on the hydrogen atoms of the ammonia molecule. So here the ammonia molecule itself acts as a base. Why it is acting as a base? The reason is in the ammonia molecule, nitrogen atom is having a lone pair. This lone pair attracts the proton from the water molecule and other molecules. So the tendency of attracting the H plus ion or donating the tendency of donating the lone pair of electrons is called as basicity. That is attracting of H plus ion or donating of lone pair is called as basicity. So here, as the lone pair is easily available, as it is easily available, as there is increase in the availability of the lone pair, the basicity increases. So here, as the all hydrogen atoms in the ammonia molecule is substituted with the alkyl groups. Alkyl groups, as the alkyl groups are electron donating groups. Alkyl groups are electron donating group, that is acting as positive inductive effect. It's showing the positive inductive effect, which increases the electron density on the nitrogen atom. So as the electron density increases on the nitrogen atom, it can attract the proton more easily. So the basicity increases with the increase in the alkyl groups on the nitrogen atom. Here, relative strength of bases. Here, the difference in the base strength in the various amines can be explained on the basis of inductive effect. That is, here alkyl groups acting as showing the positive inductive effect, increasing the increases the electron density on the nitrogen atom. In reverse case, that is, while if the minus groups which are showing the minus negative inductive effect are introduced, that is chlorine is substituted on the ammonia molecule, then the acidity basicity decreases. With the alkyl group, basicity increases. Okay, amines are stronger base compared to ammonia molecule. The reason is the amines are the alkyl groups substituted on the ammonia molecules. As the alkyl groups in substituted, as the alkyl groups get substituted on the ammonia molecule, alkyl groups are acting as showing the positive inductive effect, so the basicity increases as it increases the electron density on the nitrogen atom. So more is the tendency to donate the electron for pair for manage with to manage the proton, and more is the basic function. So as the alkyl group increases, it is easy to manage to gain the proton. So the basic nature of the amines are greater compared to ammonia molecule. More is the negative charge on the nitrogen atom nitrogen atom on the molecule is increased due to the positive inductive effect, which increases the basic nature. Okay, now thus the basic nature decreases in the order. The basic nature decreases in the order. The order is diethylamine, ethylamine, methylamine, ammonia, and chloroamine. Here dimethylamine is having a greater number of alkyl groups. Two ethyl groups are there. Your single ethyl group is there. Your methyl group is there. Here compared to methyl group is shorter. So it is having a lesser basicity. Here no substituent. Here electron withdrawing chlorine atom is substituted on the ammonia, so decreasing the basicity. The order of the basicity is shown in the table. That is, here methyl, ethyl, and isopropyl tertiary alkyl group. Here, as the methyl group is there, the dimethylamine and primary amine, as the amine groups alkyl groups are substituted, as basicity increases. But here we have one exception, that as the number of alkyl groups, that is here we can notice that tertiary amine is having a less basic nature. The reason is, as the basic alkyl groups are increased, that is number of alkyl groups are increased, the steric hindrance comes into the existence. Because of the increase in the steric hindrance, the lone pair of electrons which are present on the nitrogen atom not easily available to the proton. So tertiary amine is less basic compared to other amines. The reason is because of steric hindrance. Whereas uh, when we consider only the inductive effect, the tertiary amine should be more basic in nature, but exceptionally due to the steric hindrance, the tertiary amine is having less basic nature. Now, ammonia molecule is having pKb value as 9.5. Relative basic character of amine is not in accordance with the inductive effect, that is tertiary, secondary, and primary. If only inductive effect is considered, then the order should be tertiary amine should be more basic compared to secondary than primary. But it is in the following order, that is secondary, primary, and tertiary amine. That is due to the steric hindrance. The steric hindrance, because of the steric hindrance, what is happening? The whatever the inductive effect is getting disturbed. So the basicity will be having a quite exceptional order. Here, secondary amine, primary amine, and tertiary amine. Now, secondary amine, tertiary amine, and primary amine. This is the basic nature. This exceptional order in the basic nature is due to the steric effect. Here, methyl group. When methyl group is only the methyl group is substituted on the nitrogen atom, it is having a pKb value 10.64. As the methyl groups are introduced, two methyl groups are there, 10.77. As the pKb value increases, pKb values, as the pKb values increases, the basicity increases. Now this one is having very less basic, that is in nature, that is due to the 9.8. Here ethylamine. Next year, here is secondary diethylamine, tertiary ethylamine. Here, in the both the cases, the secondary amines, that is dimethylamine and diethylamine, are having more pKb values. So it is having more stronger basic nature. However, in the gas phase, the organization of the conjugate acid, that is due to the hydrogen atom, are absent. See here, hydrogen bonding is absent. Here, however, in the gaseous phase, in the gaseous medium, what is happening? The hydrogen bonding is absent. Because of hydrogen bonding is absent, uh, the basicity will be only in accordance with the positive inductive effect. Because of that, in alkyl groups, positive inductive effect of the alkyl groups. Because of that, the basicity of the amines follows the order with respect to positive inductive effect, that is tertiary amine is having more basic nature compared to secondary amine and primary amine and ammonia. But in the aqueous medium, secondary amine, primary amine, and tertiary amine. But in the gaseous medium, tertiary amine, secondary amine, and primary amine, then comes to ammonia. The tertiary amine is having more basic nature, that is only due to the positive inductive effect. But when we are considering in the aqueous medium, we have to consider along with the inductive effect, that is positive inductive effect, we have to consider the steric hindrance effect, which is making the order disturbed, and it is having a exceptional order, that is secondary amine is stronger basic nature compared to primary, and tertiary amine, secondary amine is having more basic nature and tertiary amine is having lesser basic. Okay, now let us discuss the next application of inductive effect, that is inductive effect and stability of carbocations. Now we have to understand about the carbocation. The carbocation is having three bonds with the other atoms. It may be hydrogen atom, it may be hydrogen atom or alkyl groups or chlorine atom, whatever be. It is having three bonds and with positive charge, and in the valence shell of the central carbon atom it is having 6 electron. As it is having a 6 electron which is less than 8 electron, so in order to complete its octet shell, it is highly reactive, that is carbocation with is positively charged, because it is having 6 electrons, and it is highly reactive species which is formed in between the reaction mechanism, okay. Now let us discuss the stability of carbocations. Now this is the methyl carbocation. Now here, with the substitution of one of the hydrogen with the methyl group, here it becomes ethyl carbocation. Here second, that is primary carbocation. Here this, when two hydrogen atoms are substituted with two methyl groups, then it becomes secondary carbocation. If all the three hydrogen atoms are substituted with the methyl groups, then it becomes tertiary carbocation. Now let us discuss the stability. Methyl carbocation, primary carbocation, that is methyl substituted with one of the hydrogen substituted with methyl group, then it acts as primary carbocation. If two hydrogens are substituted, then it becomes secondary carbocation. If all the three hydrogens are substituted, then it is called as tertiary carbocation. Least stable, and this is most stable. That is, here, as the alkyl groups, that is methyl groups, are introduced, as the number of methyl groups are increased, the positive inductive effect on the central carbon atom increases, which supplies the electron density on the carbon atom, and the positive charge get neutralized to some extent. This positive charge get neutralized to some extent because of positive inductive effect by the alkyl groups. Because of that, the positive charge get neutralized and carbocation get becomes more stable. So here in the methyl carbocation, no alkyl groups are there to supply the electron density, so it is least stable. And with the increase in the alkyl groups, with the introduction of alkyl groups on the hydrogen, with the substitution with the in place of hydrogen atoms, the E plus inductive effect, that is positive inductive effect, increases and stability of carbocation increases. So tertiary carbocation is highly stable. Now next is the carbocation is electron deficient. It is having only six electron in its outer valence shell. The methyl group shows positive inductive effect. The next is here, that is methyl group is supplying the electron density on the carbon atom. The arrow mark represents it is supplying the electron density on the carbon atom, which is making the positive charge to get neutralized and makes the carbocation more stable. Thus, the extra density is pushed on to the carbocation, which makes the stabilized carbocation.